All right, here we are, part two. We're going to talk about kinetic energy and temperature this time. So, average kinetic energy. So, the particles in any collection of atoms at a certain temperature are actually going to have a lot of different kinetic energies. But most of the particles are going to have kinetic energy somewhere in the middle, kind of around the average. Well, it would be the average, but it's a nice little peak. So if we're looking at two gases at two different temperatures, or two substances, really don't necessarily have to be gases. In this case, they have water. You look at the cold water. There are particles that have a lot of kinetic energy over here, okay, but the majority of the particles are right in here. This is the percent. So you're looking, if this was 100%, you're looking at 80% or so that have a kinetic energy way down here. Whereas if you look at the hot water, the majority of particles, like, I don't know, a little bit less than 50% of them are going to have kinetic energy right in the middle there. And that is a lot higher than this over yonder. Now, keep in mind, with the hot water, you still have particles that are not moving very fast, and then you have some that are moving super duper fast. So the kinetic energy of the particles in a substance are directly related to the temperature. So the higher the kinetic energy, the higher the temperature. But you have to keep in mind it's an average. It's not just, oh, all the particles are moving this speed right now. It's the majority of the particles are moving that speed. It's an average. Absolute zero is the temperature at which the motion of particles theoretically ceases. Now that is theoretical. We've never gotten to absolute zero, and it's a lot more complicated than that. There's more to it that I don't know enough about to go into, but theoretically, that's where we don't have any more energy. They would have, well, when I say energy, kinetic energy, they would have no more kinetic energy. The Kelvin temperature is what we're going to use when we do calculations. So Kelvin is the scale that goes from 0 on up. There's no negatives. So that way we can plug it into the equations. And the Kelvin temperature is going to be directly proportional to the average kinetic energy. So the greater the kinetic energy, the greater the temperature. So now let's start looking at our different phases. The first one we want to look at is liquids. So we've talked about liquids before, but substances that can flow are referred to as fluids, but liquids and gases are fluids. The reason for this is because the particles are not so tied together like they are in solids. Solids have like a nice crystal structure. Liquids don't. They'll take the shape of their container, but if you remember, they do have a definite volume. So they are still sticking to one another. It says particles are attracted to one another, intermolecular forces. Well, intermolecular forces are the forces between molecules, hence intermolecular. So that means the particles still have enough attraction to one another that they're going to stick fairly close together. With gases, no. They've broken that. They're out on their own. To escape a liquid and become a gas, a particle must have enough kinetic energy to overcome the intermolecular forces. So like I said, those forces between the molecules are what's holding it together. As soon as a particle gets enough energy to break those attractions, it will. It'll go off and become a gas. And then, as I said before, gas particles are not close together at all. The interplay between the disruptive motions of particles in a liquid and the interactions among the particles determines the physical properties of liquids. All right, so you're looking at how the particles are attracted to one another and how they bump into each other, how they stick together, all that sort of deal. So this brings us to evaporation. What is the relationship between evaporation and kinetic energy? Well, like I said, for a liquid to become a gas, you have to break those intermolecular forces by getting enough energy. So how do you get something to evaporate? You give it energy, enough energy to overcome those intermolecular forces. This is called vaporization, the conversion of a gas, conversion of a liquid to a gas, sorry. Gas and vapor, you can pretty much use them interchangeably. We typically call something a vapor if it's usually a liquid. So that's really the only technical difference between them. When this happens, we call that evaporation. Now, with evaporation, we're talking about this happening on the surface. So, for instance, if you have a cup of water, evaporation is happening on the surface of that water. Now, if you have like a beaker or something, you put that on a burner, you start heating it up, and then it boils. That's not evaporation, that's boiling. Now, is evaporation still happening on the surface? Yeah, of course. But there's a difference between boiling and evaporation, and that difference is that evaporation happens on the surface of the liquid. So, in an open container, when you set a liquid down, the gas particles from evaporation, they're going to escape. And so if you set a water bottle down with the lid off, eventually, theoretically, it would become empty. It'd just take a very long time. If you have a closed container, those molecules can't escape. And so they eventually will reach equilibrium. So when you have like a water bottle with the lid on and you've had half of it or so, it is still evaporating, but it's also condensing at the same time, and it reaches equilibrium, so it condenses and evaporates at the same rate. And so you don't see fluctuation in the water level. You don't even notice anything's happening at all, but evaporation and condensation are happening at the same time. So that's kind of cool. During evaporation, only the molecules with a certain minimum kinetic energy can escape the surface of the liquid. What's that minimum kinetic energy? Well, it's the kinetic energy required to break those intermolecular forces, the attractions between the molecules. Now, it says evaporation is a cooling process. Well, how does that work? Well, in order to evaporate, a molecule of liquid needs energy. So it would have to take energy in order to become a gas. So you sweat. You get all this salt water all over you, seeping out of your body. Well, why does your body do that? It does it to cool you off. Well, how does that work? Once you have all this salt water all over you, it's going to evaporate. Well, how does it evaporate? It uses the energy from your body. You've been working out or doing at least some sort of activity. It's going to take the energy from your body and use it to go from the liquid state to the gas state. So it's going to take energy from you, which is going to cool you off. So it's really cool. It's something that your body does to help you cool off, because evaporation will take that energy away from your body, and then you will feel a lot better after that. Sometimes you get a little too cold. This is also why when you get out of the shower or something, or you jump in the pool and get out, it's cold, because that water that's on your body is going to evaporate and it's going to take your energy, so it feels cold until you can get back in. All right, I'm going to save vapor pressure for next time. I hope that this was good for you, and go ahead on to part 3 if you're ready.